Welcome once again for the third in series of the Samvaad talk series, showcasing our institutional research. So today we have a talk by Professor Ashish Choudhury on his research work on secure multi-party communication. And many of you are already familiar with his work and the cutting-edge work that he's doing. It's also very gratifying and kind of humbling for us to note that Professor Choudhury recently suffered some kind of personal loss, and in addition, he also has a class at this time, and he has accommodated both. Despite all that, he's come here and agreed to give his talk on schedule. So this is the spirit in which we are basically pursuing our research. That we take it very seriously, and in terms of we are very passionate about work. So I'd like Professor Muralidhara to chair this session and start with an introduction to.
So I don't think Ashish requires an introduction, but in case if you don't know him, he got his PhD from IIT Madras. Then he did some few postdocs, mostly at University of Bristol. After that, he has been with us for the last 3.5 years, and he's going to take you to the world of secure multi-party computation. So probably this section course could be mostly informal, just like your class. Please feel free to ask enough questions as and when you have questions. Okay, over to us.
Thank you. So hello everyone. Here is the talk agenda. So I have roughly divided my talk into two parts. So the first part is going to be a very gentle introduction to my area of research, where I will be talking about what exactly secure multi-party computation is and what are the various dimensions in which we can study this problem, what's the significance of this problem, and so on. And part two is conditional, in the sense, if time is left, which I will ensure is not, and if you are bored, which I will ensure you do get, then I will discuss one of my recent works in detail. So this partially answers Amit's question. So before I was coming here, he was asking me whether we will understand anything or not. So part two is for you. Part one is for you. Part two is for the general audience. Okay. So let's begin the talk. So we are all in the age of information, because information, or the so-called term data, is floating everywhere. So we have data associated with individuals, like his age, salary details, bank details, and so on. We have information or data associated with organizations like IBM or TCS, for example, the list of their employees, their profit, loss, turnover, etc., etc. Every educational organization have their information associated with them. Hospitals have their own data associated with them, for example, the list of patients, their medical history, and so on. And you consider any organization, any entity in the current world, they have some data associated with it, because data is everywhere. That's why we are doing big data analytics, right? But since there is so much data floating around, the security concern or the privacy concerns are also there. For instance, for every entity, some kind of private data is available associated with that entity, which that entity would not like to be made public. So for example, if I consider the individual, no individual would prefer to disclose his Aadhaar number in public. So it's a big debate whether the way Aadhaar is implemented today, it leaks your Aadhaar number or not, or no individual would be interested to make his biometric traits or his genome signature, etc., available in the public domain. In the same way, no hospital would like to disclose its medical records in public. It won't prefer to disclose the details of the patient, what kind of diseases it suffered from, and so on. And the list goes on. So since we are in the age of distributed computing, internet is brought so many advantages and disadvantages. In the context of current computing scenario, there are lots of applications where we come across the following problem. We have a set of mutually distrusting entities. So let me call them P1 to Pn. They do not trust each other, and each of these entity has some private data associated with it. So you can imagine that P1 has some data X1, P2 has some data X2, and so on. And they do not trust each other. That's why they are not willing to reveal their data in the public domain or to each other. But at the same time, you can say that they want to compute some joint function or computation which takes all the data from the individual entities. So in some sense, we want to compute this function f on the combined data by keeping the individual data as private as possible. And this is specifically the problem of secure multi-party computation, because you have multiple entities, each entity has some private data, and they together want to compute some function on the combined data by keeping their data as private as possible. So this problem is also known as computing on private data, because you want to compute something which is very private with each individual. And you can see that we require two conflicting goals here. We require the availability of the data as well as the confidentiality of the data, because until and unless the data is not available from each and every individual, you cannot compute the function. So availability is required. But at the same time, you would like the confidentiality, because you do not want to reveal the individual data. So these two are like conflicting requirements. So the analogy that I can give to you is like, if you have jewels, you can always keep your jewels safe by keeping it in the locker. So that solves the confidentiality part. But at the same time, you would like to show them in the public domain if you're going to a party, right, or some occasion. So that's the availability part. So we require both the requirements to be simultaneously solved here. And if you are thinking that encryption will help you to solve both the problems, well, that's not going to help, because if you simply encrypt your data, that serves the confidentiality part. But at the same time, you want to compute on the clear data. You cannot do the computation on the encrypted data. So encryption is not going to help you in the current scenario, right? So now you might be wondering, yeah.
So what would be an example of?
So I'm coming to that. So now you might be wondering where exactly we come across this scenario where there are multiple distrusting entities and they would like to compute some function on the combined data. So now I'm going, for the next 10 minutes, I'm going to give you lots of practical applications for the scenario, right? So let's start with the simplest scenario, namely privacy preserving data mining. And imagine that we have a set of n hospitals, and each hospital has its own private record, and say they want to do a data mining operation on the combined database. For instance, they might be interested to find out how many people across all the n hospitals or all the 3 hospitals are suffering from a particular disease, or is there a common patient registered across all the hospitals and so on. So that's kind of function which you want to compute on individual data, and your individual data are the three medical database here. Of course, if each hospital can disclose its entire database in the public, then this problem is very easy to solve. You have all the 3 database in the public domain, you can run your usual data mining operations, but your goal is to hide the individual database as much as possible, right? You can consider the problem of secure e-auction, say where the goal is you have a set of n bidders and they would like to bid for a valuable object, right, without disclosing the exact value of their bids. So the function that you would like to compute here is the max of the n bits, but in the process you would like to keep the individual bits as private as possible. It's fine if you learn that your bid is finally greater than or less than the winning bid, but that's fine. That's not a security breach. You want to hide the exact value of individual bits. So that's the function you want to compute. So the function that we want to compute here is the max function, right?
So is it that you just want to see there are, yes, I mean I could imagine there's at 2 levels, right? One, the individual bid values are known, but the source is not.
Yeah, so
the other where you also don't want the values to be known, you only want the final value.
So we can have both the aspects depending upon the problem that you formulate, right? If you want to hide the source of the data as well, that's a higher level problem. But right now we know that, okay, some data is coming from this guy, some data is coming from this guy. That source, the identity of the source is known, but we do not want to disclose the bits information about the individual data. Right? But what you are saying is a more generic version of the problem. Right? You can consider the problem of secure online dating. So for instance, there might be 2 friends and they might be interested to find out whether they are mutually interested in each other or not. Of course, they cannot say it directly over the other's face because that might be embarrassing. So any idea what function of their individual choice bits they would like to compute here? So B1 denotes whether this entity likes the other entity or not, and same for B2. So which function they would like to securely compute here? And, not XOR actually. Right, so we would like to securely compute here the AND function by keeping the individual choices as private as possible. Right, And this is a very ambitious application of secure MPC, which has been recently acknowledged by DARPA, and this is like in their list of things that they would like to do in the next 5 years. So imagine that two so-called neighboring countries or rival countries launch their spy satellites, right? And since they are launching their spy satellites, they cannot make the details of their trajectory information or orbit information in the public domain because that's a spy satellite. But since both the countries are launching the satellites without knowing the orbit of the other country's satellite, what's going to happen is it's quite possible that collision occurs because both of them are launching their satellites without knowing the exact orbit information of each other. And if such collisions occur, it's going to be enormous amount of loss. If you just search in Google satellite collisions in space, there are so many occasions where such collisions have occurred in the past, right? So again, MPC can help you. So the MPC problem that we can formulate here is we have two countries. Their private inputs are their trajectory information, and the function that they would like to compute is how close their trajectory information are within each other. So that's a function they would like to compute without disclosing the exact information about their individual trajectory information. We can have privacy-preserving pattern matching, namely the so-called client-server scenario. So you imagine that I am a client and I have a sample. It can be a biometric sample, it can be a face sample, it can be any kind of sample you can think of, and there is a server who have database available with it, and I am interested to find out whether this sample is present in the database or not, without disclosing any information about the sample or without learning any additional information about the individual contents of the database, right? So this is like the privacy preserving pattern matching, and this encompasses lots of interesting problems which you can formulate in the so-called client server setting. Another interesting application is privacy preserving ML. So now you might be wondering what ML has to do in an area of cryptography, right? So according to me, doing some sort of ML is absolute necessity for surviving in the current academic scenario, right? So the problems that we would like to consider here is, we know in ML, the basic idea is that you do some kind of training, and based on training you have a model defined, and once the model is defined, then in the near future, whenever any sample or any data comes, based on the model you determine the predictions, right? And the whole accuracy of your ML algorithm will depend upon how strong is your model, how strongly you have done the training phase, right? So if you have more and more data available with you, your model is supposed to be more and more stronger. So imagine that there are three mutual competing organizations, say Amazon or Google, or three entities who have their own data, and you want to do the training based on the combined data and finally want to decide the model. And then based on this model, you want to do your ML algorithms. So the question that we would like to answer here is, can this entire thing happen in a privacy preserving fashion where you do not disclose any individual information about the individual data, but at the same time your model gets constructed in a combined fashion and your model remains hidden. That means no one learns the exact contents of your model. It's still kind of shared or splitted among the multiple entities, and then you run your ML algorithms. So according to many cryptographers and even in the ML community, this can be the futuristic ML. And if you don't believe me, you just search for some of the recent papers which got published in top venues in ML like ICML. This is one of the problems which started getting addressed there, right? So I can also formulate the problem of secure cloud computing. So in cloud computing, the scenario is that you have a computationally weak client which has some function which it would like to compute on some data X, and since it's computationally weak, it cannot carry out a computation on its own. But what it can do is it can outsource the computation to a cloud service provider who says that, yes, I will do the computation on your behalf, instead you give me some payment, right? So this sounds very cool, but there are certain problems associated with this scenario if the server itself gets corrupted, because you are leaking your entire data to him, you are outsourcing your entire computation to him, so he knows your data as well as what computation you would like to carry out. And at the same time, it's not guaranteed that the service provider is indeed carrying out the computation correctly, because he must just be interested in building his revenue. right? So he may outsource the actual computation to someone else if someone else is paying him a more price. He may simply give you back some junk answer. How do you verify whether the answer or the output of the computation is the right output? You cannot redo the computation yourself because that simply loses the purpose of cloud computing, right? So again, MPC can come into rescue here. What you can do here is, since anyhow you are willing to pay because you cannot do the computation on your own, why don't outsource the computation to 3 different service providers instead of outsourcing it to only one service provider? So you just share your data. So share is not simply splitting. That means the one half of the data to one guy, another half. It's a sharing in a cryptographic sense. So you share your data among multiple service provider, and whatever computation one single server was supposed to carry out, they can now carry out the computation together jointly on the shared data, and the privacy of the data and the robustness of the computation will be guaranteed as long as majority of the service providers are honest. So you no longer have to worry about the privacy of your data as well as the robustness of the computer, provided majority of the service providers are honest. Of course, you are increasing the overhead here because you are now paying thrice compared to the original solution, but at the same time you are getting the privacy of your computation and the robustness of the computation.
So in this example, that is how any communication between the
servers, yes, that's required. So now they have to run an MPC protocol among them.
Okay, but in that case, what would that mean?
So that's why I'm assuming that as long as majority of the service providers are honest.
Or not just 1/3.
Yeah, even for half it will work. Even if for half it will work. Right? And there are several applications where the entire security of the application is compromised because you have the so-called single point of failure. And yeah. Active adversary. Yes. Right. So there are several applications where the security of the entire application simply depends or simply fails because there is a single point of failure. Namely, you store your entire secret information or credentials at a single place. Imagine you simply store your decryption key at a server and the server gets compromised, and as a result the entire application is compromised, right? So how do you prevent such single point of failure, right? So again, MPC can help you. So instead of storing the credential or the secret information at a single location, you can split it or you can share it across multiple servers who might be running different platforms. One might be running on Windows, one might be running on Linux, and so on. And now whatever application or function was supposed to be carried out by the original signing credential or a secret information, the same functionality now will be carried out by running a joint protocol between the servers. So now the life of the attacker becomes difficult because earlier in the single point of failure he has to compromise only one server, but now he has to compromise more than one server, and assuming that he cannot do that simultaneously, the security of your application retains, right? So you can see that there are lots of problems which can be captured by this general framework of secure multi-party computation, and behind all the applications that I have discussed till now, there is a common abstraction. So as a theoretician, we would like to have a common abstraction which can abstract all the applications problems that I have discussed till now, and this is the common abstraction. You have a set of n mutually distrusting parties. They might be present across different corners of the world, and each entity has some private data. I call it a XI. It can be their database, it can be their medical record, it can be anything. And there is a common n input function f, and the goal is to design a protocol according to which the participants talk to each other, and such that finally at the end of the protocol they learn the function output. And we would like the following two properties to be achieved by the protocol. First is of course correctness. We would require that even if there is a subset of parties who are deviating from the protocol, they are behaving maliciously, still we would require that the good guys, they should obtain the function output. And we would require the privacy, namely we would require that the bad guys should not learn anything additional. That means we would like to ensure that whatever the bad guys could learn from their own input and the function output, only that much should be revealed to them, nothing additional should be revealed. That's a loose or informal privacy requirement. Right? And it's like the Holy Grail problem. It abstracts all the secure distributed computing tasks that we have seen now. And if we have a solution, efficient solution for MPC, then we have solution for many secure distributed computing applications. So notice that MPC would have been very easy to solve if we have a so-called trusted third party, right? So imagine that there are n entities and there is a so-called trusted third party who is trusted by all the n entities. Then the MPC problem is very trivial to solve. Namely, each entity could have given its input to the trusted third party, and since the trusted third party is trusted by everyone, he won't reveal your data to anyone else. And he knows the description of your computation, so he can carry out the function on his own, and he obtains the function output, and he can reveal the function output to everyone else. So this is like the best or ideal secure protocol that you can think of. But the problem with this approach is you are actually creating a single point of failure, right? What if the trusted third party is compromised? And the whole goal of secure MPC is actually to get rid of this single point of failure, right? And trust is very rare and very volatile in this Kali Yuga, right? So we cannot trust anyone. If you could have trusted anyone, then MPC, rest in peace. So in a nutshell, the whole purpose of a secure multi-party computation protocol is the following. It says, it guarantees that whatever computation you can carry out in the presence of a trusted third party, the same computation can be carried out in the absence of a trusted third party by executing a protocol among the entities themselves. That means whatever level of security you can achieve in this ideal world MPC protocol, a real world MPC protocol ensures that the same level of security is achieved even in the MPC world. That means whatever bad guys could have learned in this ideal world protocol, the same amount of information the bad guys would have learned even by participating in a real world MPC protocol. But in this ideal world MPC protocol, the bad guys learns nothing. As a result, they end up learning nothing even in the so-called real world MPC protocol. So that's loosely how we formulate the security. What do we mean by learning no additional information? By learning no additional information, I mean whatever the bad guy would have learned by participating in this protocol, the same amount of information he should have learned by participating in a real world protocol where the participants talk to each other, right? So here's a little bit about the history of MPC. So the problem was first formulated by Turing Award winner Andrew Yao in his seminal work in 1982 Fox paper, where he introduced the so-called Yao's millionaire problem. So the problem description is, say you have two millionaires who due to some reason are not in talking term with each other, but at the same time they would like to find out who is richer between them, but they are not interested to disclose the exact value of their asset to each other, right? So you can clearly see the function that you would like to compute here is the max function or the min function. It's fine if I learn at the end of the function that my asset is greater than or less than your asset, but what I should hide here is the exact value of the asset. So the function that you would like to compute is the max or the min. So he formulated this problem and then he showed that how any two-party function can be securely computed in the presence of an adversary who is corrupting one of the entities in a passive fashion. And MPC is one of the most widely studied problem in both cryptography community as well as in the distributed computing community. So I would like to say the following, that these are the so-called Turing Award winners who are cryptographers, and all of them have contributed in some fashion to this very fundamental area of research. So you have Adi Shamir, who gave us the notion of secret sharing, non-interactive zero knowledge. You have Manuel Blum, who taught us how to do coin flipping over the telephone, namely how to do the coin tossing over a telephone. We have Shafi Goldwasser, who gave us zero knowledge information theoretic multi-party computation, and we have Silvio Micali, who taught us randomized Byzantine agreement, randomized generals. We have Andrew Yao, who actually formulated the problem itself and gave us this fantastic notion of garbled circuits. And of course, we have Michael Revin, who gave us oblivious transfer, randomized Byzantine agreement, and so on. So what happened to be a theoretical area of research in 80s and late 90s has now become a huge topic of research. And if you take any flagship crypto conference or security conference, say Eurocrypt, Crypto Asia Crypt, or any security avenue like IEEE, S&P Oakland, or ACMCCS, one of the widely studied topics is MPC. In fact, the community is increasing it's becoming so large that there is a recent proposal in the ISCR body. ISCR is the International Association of Cryptographic Research. A proposal has been made that we should soon start a conference only on MPC. So you can imagine that's the importance of this problem. Right. So now I have introduced you the problem statement. What's the motivation of the problem? In the next 10 minutes, what I'm going to do is the following. So in the battlefield of Kurukshetra, Lord Krishna, he showed his divine roop, right? Where he showed his infinite dimensions. And the dimensions were so infinite, like even a great warrior like Arjuna got scared. So what I will do in the next 10 minutes, of course, can't become Krishna because I am one of his creatures. What I will do is that I will just discuss the various dimensions in which we can study this problem, the MPC problem. Right? So let's start with dimension 1, namely what kind of functions we can compute and how do we represent those functions. It turns out that any polynomial time computable function can be securely computed in the presence of MPC. That much guarantee any MPC protocol provides to you. But now the question is, how do you represent your function f, which the parties would like to compute? And now you have 3 sub-dimensions. You can either design a protocol which is tailor-made to a given type of function. Say for example, if you want to do privacy-preserving ML, here is the protocol for doing privacy-preserving ML. If you want to do privacy-preserving pattern matching, here is the protocol for privacy-preserving pattern matching and so on. That means depending upon what is the specific function you want to securely compute, you design a tailor-made MPC protocol for that. But that's not good, right? As a theoretician, we would like to design a protocol which is very generic and very abstract. And it should work for any kind of function irrespective of what exactly is the function. So if we are interested to design a generic MPC protocol, we have to come up with some abstract representation of the function. And there we have 2 kinds of subdivisions. Either you can represent your function as a Boolean function, where you assume that the entire computation is a sequence of several kinds of Boolean gates, starting with your input layers where the participants feed the input. Or you can represent your function as an arithmetic circuit over some arithmetic field, where we have only 2 kinds of function, 2 kinds of computation supported, namely say plus and dot. And it's a very fundamental fact that any computable function can be either represented in this Boolean world or it can be represented in the arithmetic world, right? So on a very high level, once you fix the representation of your circuit, what the MPC protocol does is the following. It simply evaluates this circuit in a secure fashion. What does that mean? So if assume x1, x2, x3, x4 are the exact inputs of the participants. You have say 4 participants and their respective inputs are x1, x2, x3, x4. If by some mechanism the exact value of x1, x2, x3 and x4 are known to you, that means you know the values in clear, then carrying out a computation of this circuit is an easy task because you know the value of the input gates and you know the circuit description. You can start evaluating each and every gate and you can reach the output layer. That's the function output for you. But that's not we are going to do because our goal is to hide the input values. So what an MPC protocol would do is, it would still evaluate the circuit in such a way that the bad guys or any entity would not know the exact value of the gate output for any of the intermediate gates. So you can imagine a computation as a sequence of state transformation. You start with an input state which is determined by the inputs of the participants, and depending upon the type of the gate, you go to the intermediate state. From that, depending upon the type of the gate, you go to the next intermediate state and so on, and finally you reach to the output state where you know the output state. That's the function output. That's the circuit evaluation in clear. What an MPC protocol will do is, it will simply hide the state information at each level, starting from the input layer. That means no one will know the input layer or the input state. It will be somehow shared among the entities, such that the partial state information which is available with the bad guys, it's useless for him to learn the exact state information. And after that, depending upon the type of the gate, you keep on generating the shared state after each other. And once you finally reach to the output layer, you disclose the state. By doing this process, what's happening is each of the intermediate level of computation is kind of shared among the entities, and the partial state is useless for the bad guys. That's what, in a nutshell, any MPC protocol does. Now, depending upon whether your function is represented in your Boolean fashion or in the arithmetic fashion, the way you split your state and how the way you go from one state to the next intermediate state, that differs. And that determines the overall MPC of your MPC protocol. One protocol might be doing the state transformation in a less efficient way. Another protocol might be doing it in a more efficient way. Right? So now once you have two ways to represent your circuit, the next question that you would ask is which kind of representation is better? Whether I should do the computation over the Boolean field or the Boolean circuit, or should I represent my circuit in the arithmetic domain? And the answer depends upon what exactly is the function that you would like to compute. So for instance, if my function is the summation of two numbers from F5, namely summation of two 3-bit numbers. So F5 is a finite field consisting of all 3-bit numbers, you can imagine like that. If my goal is to add two 3-bit numbers, I can represent it as one arithmetic operation in F5. So that's like saying that I want to do one addition over the field F5, and that's my circuit. Whereas if I would like to represent the same circuit in the Boolean domain, then I can do that, because that's simply a binary adder for 3-bit numbers. But then the number of gates that I would require increases, because I need to do the bitwise addition of each bit, take the carryover, and that will be reflected in the next bit, and so on. So even though I can represent the same computation in the Boolean world as well, the number of gates that I would end up having in my circuit will be too much, right? So if it's an operation like addition and so on, it's better suited to represent. It's better to represent it in the arithmetic world compared to the Boolean world. But if you want to do nonlinear operations, say for example comparison and sorting or operations of that form, it's better. Those kind of operations can be better represented in the Boolean world compared to the arithmetic world. So you have two kinds of representation, and depending upon the function that you would like to compute, you choose the notation, right? And it turns out that both the worlds have huge amount of work. We have several protocols for the Boolean circuits, we have several protocols for the arithmetic circuit, and this is a new line of work which I also started investigating, that can you do something best of the both world? In the sense, can you represent your function as a overlapping sequence of one portion where some portion is done in an arithmetic fashion, some portion is done in a Boolean fashion, depending upon which part you can do better in which world. And then you keep on changing the switching of the state, which is encoded in the arithmetic world, into a state in the Boolean world, do that computation in the Boolean world, and again switch back to the arithmetic world and do the next portion of the computation in the arithmetic world, and so on. No one explored this line of research. This is a very recent line of work, started with this NDSS 2015 paper, where they considered this notion of mixed protocols, where instead of evaluating the entire protocol in one domain, you just do an execution in a mixed fashion. Depending upon, you identify which portion of the circuit can be done in a better fashion in which world. You have to change the representation, yes. So that switching has to be done. So in this paper, they have shown that if you evaluate a function in total one fashion, in a completely one world, compared to that, if you do the same thing in a mixed world, you achieve efficiency. So they have the concrete empirical numbers as well to support that fact. Right. So that was dimension number one. How do you represent your circuit, or how do you represent your function? Dimension two is what type of network you are having, right, at your disposal. And here we have various other subcategories. So let's start with the simplest one, whether your network is a complete network or whether it's an incomplete network. When I say complete network, we assume in our protocol that each participant can talk to every other participant. That means they have a dedicated channel. And when we say incomplete network, that means we do not have a dedicated pair-wise channel between every pair of entity, right? And it turns out that most of the work in MPC is in this model, whereas incomplete network is very, very less explored. So complete network is simplified assumption, but it works only for applications where you have less number of participants, say up to 10 participants, where it's feasible to assume that you have a complete network of 10 nodes. And it's more practical applications are well modeled by the incomplete network, but we have a very poor understanding of what kind of secure functions we can do or evaluate in the incomplete network setting. So that's like a huge amount of research which we require in the incomplete network setting. Now continuing with the type of network, the second subdivision will be whether the parties who are participating in the protocol, they are part of a synchronous network or they are part of an asynchronous network. So synchronous network, we have this simplifying assumption that you have a notion of global clock and you have strict upper bounds on the message delivery. That means in a synchronous protocol, if there is a receiver who is expecting some message from a sender, he knows how long he has to wait for the message. And if the message does not reach within that time, that means suppose if the sender gets corrupt and he decides that I won't send a message, receiver knows how much I have to wait. If the message does not reach within that time frame, he can accuse that you are a corrupt guy. You are a corrupt guy. But in asynchronous network, you don't have this notion of global clock, right? The clocks are loosely synchronized and messages could be arbitrarily delayed. You can't put an upper bound that, okay, within this much time, the message should definitely come. You can never do that. And most of the real world networks like the internet are more appropriately modeled by the asynchronous network model. So now let's consider the same scenario, the same sender receiver scenario in the asynchronous model. And here the receiver does not know how long he has to wait for the message. Now there can be one of the two possible cases. Either the sender is corrupt and he has not sent a message, or it might be the case that the sender has sent a message, he is honest, but the message got arbitrarily delayed due to network congestion. So if you look from the viewpoint of the receiver who is honest, both these scenarios are equivalent. He don't know what is the case. And if he simply waits for the message X, the wait may turn out to be an endless wait and your protocol will never terminate. Consider the following setting. Imagine an asynchronous protocol among n parties and say T of them are bad. T is the upper bound on the maximum number of guys who can be corrupt. Then you can see that at any step of the protocol, no party can afford to receive communication from all the n parties. Because if this receiver simply waits for the communication or message from all the n parties, then it may be the case that there are T bad parties who have not communicated to you and you are simply waiting endlessly for the message, right? So the way out for this receiver is as soon as it receives communication from n minus T parties, it has to think in its mind that the communication from the remaining T parties are not going to come and it has to go to the next step of the computation.
Yeah, what do you formally mean by cheating here?
Which is he does not send a message. So that will be the fourth dimension. How do you model the corruption? Okay, so right now I am just cheating in the sense that he crashes. He simply does not send a message. You think like that, right? So from the viewpoint of this receiver, as soon as it receives communication from n minus T parties, it has to start doing the next step of the protocol. But in this process, what it has done is, it may ignore the communication from T potentially honest parties. That means the T communication or the T messages which have dropped may belong to the honest parties and that may come very late. He cannot wait for that period because he don't know whether that will happen or not. Worse, what may happen is, this is the viewpoint of one receiver. This is the viewpoint for each individual receiver. That means the set of T dropped messages will be different for different set of honest parties and for different steps of the protocol. And as a result, you can see that designing completely asynchronous protocol is a very, very challenging task because of this inherent phenomena which you can never deal with in a completely asynchronous network, right? So these are the two extreme ends, synchronous and asynchronous. Most of the works are in this simplified synchronous model, and the asynchronous model is very less explored, even though it models your real world network like internet appropriately. And it turns out that there are many nice, interesting impossibility results. That means there are several things which we can never do in the completely asynchronous world, which could have been carried out in the synchronous work. For example, there is this seminal result by Fisher, Lynch and Patterson called as FLP impossibility result, which shows that even if you have a single crash failure, you cannot solve a simple problem like agreement, right? So the way out is, as you were suggesting, we can have some kind of partial synchrony assumption or hybrid setting where we assume that, okay, our network will not be completely asynchronous. You have some kind of partial synchronization available for few initial rounds, say 1 round or 2 rounds. Within that 1 or 2 rounds, you do whatever you can do, and after that your network is completely asynchronous. That motivation for this hybrid network is, can we get rid of some of the impossibility results that we get in the completely asynchronous model? And this hybrid network is again very less explored. So one of my research works or my current research direction is mostly focused on this hybrid network setting where goal is to identify what can be securely done in a hybrid network, which was not able to do, which we cannot do in a completely asynchronous setting. Right? So that's the second dimension. We have type of network. That's the second dimension. Dimension was what's the representation of your function. Now the dimension 3, to answer your question, how do we model trust and distrust in the network? What do we mean by cheating here? Right? So first of all, bad people always work together. Right? So that's why in MPC or in any distributed computing task, we assume that the distrust in the network, it is modeled by a centralized entity, say adversary, who is going to control certain subset of the entities. How it is going to control that subset and how that subset is defined, that will be the other subdimensions. So let's go into that, subdimension number 1, namely what kind of adversary you can have. So we can have either threshold adversary or non-threshold adversary. So threshold adversary means we specify that out of the n parties, adversary is going to corrupt T entities. So T is the upper bound. Which T entities are going to be under the control of adversary, you won't know. As a participant of the protocol, I will know that among the n entities, T participants can be corrupt. Now I have to design a protocol which should take care of those T corrupt entities. That's the threshold model. And a more generalized version of this threshold model is the non-threshold model, where we don't have any such upper bound. Instead, we give so-called adversary structure, namely subsets of potentially corrupt guys. And during the protocol execution, any one such subset may actually get under the control of the adversary, and it may control that particular subset of the bad guys, a subset of the entities. So you can imagine that if I have 3 entities, then one subset of corrupt guy could be P1, or another subset could be P2 or P3, P2 combined with P3. During the actual execution of the protocol, whether it is this subset or this subset, that information I will not have, but I will know beforehand that these are the potential subsets of entities which might collude together to cause harm in the protocol. So that's a more generalized form of the adversary. So again, it turns out that most of the work is in the threshold model because of its simplicity, and we have very poor understanding of MPC protocols in the more generalized adversary setting.
Non-threshold doesn't mean that P1, P2, P3 are identified beforehand, we just don't know what.
Yes, they are identified beforehand. Yes, the subset is already given to you. So you can imagine it like this, in a bigger project, you would like that, okay, only manager should not have access to the full project, or these 2 entities should not have access to the full project, and so on.
So what if I take a pessimistic assumption and assume all of them are...
Then you cannot achieve any kind of security.
No, will it become identical to a thresholding?
No, so threshold model is a special type of non-threshold model where the size of each subset is upper bounded by T.
But the subset is not.
Yes, but the subset is not. Exactly. Right? So that is subdimension 1. Subdimension 2 is what kind of computing power your adversary has. Are you assuming that he is polynomial time bounded, or are you assuming that he is computationally unbounded? So if I am assuming that my adversary is polynomially bounded, then I can make use of Soha. Yeah.
So, yeah, when you have these subsets, what you need is an OR band.
OR. So within you have an OR of either this or this or this or this. Within that and yes. 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 Yeah, it's a Chomsky, the CNF or DNF? It's DNF, yes. Right. So when I am assuming my adversary is polynomially bounded, that means I assume that he cannot carry out any kind of exponential computation, or you do not have access to quantum computers or stuff like that. And as a result of that, I can use many nice cryptographic tools like encryption or public key cryptography in my protocol. Whereas if I am assuming my adversary is computationally unbounded, that means I am assuming he can even carry out exponential amount of computation, he can solve any problem, he can solve factoring, he can break RSA and so on. And interestingly, we have both kind of protocols available in the literature. We have MPC protocols whose security is only against computationally bounded adversary, and we have a very nice body of work. They are called information theoretically secure MPC, which provides a security guarantee even if your adversary is computationally unbounded. And this is the third subdimension against under the type of adversary, whether your adversary is semi-honest or whether your adversary is malicious. So semi-honest or passive adversary means that the bad parties, they are only eavesdropping your computation, that's all. That means it's only eavesdropping the computation of the bad guys. It's not deviating from the protocol instruction. That means as part of the protocol, if it is supposed to send a value X, it will send value X. It won't send X dash. But its only aim is to learn something more in the protocol. That's what is a semi-honest adversary. Whereas an active or malicious or Byzantine adversary is the most powerful notion of adversary, where the bad guys or the adversarial entity can deviate from the ideal behavior in any arbitrary fashion. So it may stop communicating, it may send you wrong values, or it may behave in any arbitrary fashion. So that's the strongest form of adversary you can have. So again, both these adversarial models have been very well explored, and the starting point of any MPC protocol is the passive adversary, because we do not directly attempt to design a protocol against a more stronger malicious adversary. We always aim for security against a passive adversary, and then on top of that passive adversary we add additional tools to make that modified protocol even secure against the more powerful malicious adversary, right? Now I have another possible subdivision here, whether your adversary is static or whether your adversary is adaptive. So static adversary means that the adversary decides the bad parties at the beginning of the protocol itself, at the onset of the protocol itself, whereas adaptive adversary means it can decide which parties to corrupt on the fly as the protocol proceeds, depending upon whatever communication it has still at a certain point of time.
As part of the general problem definition, you assume that any communication that happens between two parties is private to them.
But that depends upon whether your adversary is computationally bounded or unbounded. If you are using cryptography, then we assume that he can see communication between any pair of entities, even the communication between a pair of honest guys. That communication will be encrypted. So as a result, it cannot see the contents of that message.
Yeah, but whatever bits and bytes are flowing,
that he can see. That also he can see. Whereas in the information theoretic MPC, he do not have any access to the communication between pair of entities. Yes, yes.
So in that case, what does that say? Yes, earlier slide.
Yeah.
You said passive observer eavesdrops the corrupted party.
Yeah.
If it's public anyway, what does it mean to eavesdrop on?
Okay, so if I go into Byzantine model, so it's not only having full control over the corrupt entities, it can dictate him in whatever way it can behave. So if it is supposed to send a value X, it may end up sending X dash. It's not only eavesdrop, but on top of that, you also start sending ill-formed messages, bad messages, or may not send messages at all. All those kind of behavior are Byzantine behavior. If it's in the cryptographic model, he is seeing the communication between honest guys which is encrypted. So even though he's seeing the encrypted packets, even though he's seeing the packets, he cannot see inside the packets.
But for the corrupted parties, he can see.
Yes, yes, yes. Right. So static adversary means that a set of bad guys will be decided at the onset of the protocol itself, because before the protocol starts, whereas adaptive adversary means adversary can corrupt the bad guys during the runtime as the protocol proceeds. So the way you can imagine, you can distinguish between static and adaptive adversaries. If it's a two-party computation, and if I say adversary is static, where it can corrupt one of them, then it has to decide before the protocol starts which party is going to corrupt, whether it is P1 or P0 or which party. That's a static adversary. And once the protocol starts, he has to stick to that corrupt guy. He cannot later change it. Whereas adaptive adversary means he can see what communication is going on, if I am say in the encrypted domain, and depending upon what's going on, he can decide it's better to corrupt this guy compared to this guy. So that's the adaptive nature of corruption, right? And adaptive adversary, as you can see, it models our real world networks, real world attack strategies, real world adversary in a more realistic fashion, because when we say an adversary has hacked our network, he does not decide to hack before the protocol starts. Before the protocol starts, some communication starts happening, and adversary actually sees the communication among the entities, and then it decides which node to corrupt. So that's the adaptive nature of the adversary, right? So both these models are there, and most of the work is in the static adversary model. And adaptive adversary model, even though it's a more generic form of the adversary, it has been very less explored, because as soon as I make the assumption that my adversary is an adaptive adversary, it adds lots of complexities in my problem description. So the way out is you can assume semi-adaptive adversary or one-sided adaptive corruption, where you assume that one of the entities will be static corrupted, other entity will be semi-adaptive corrupted. So that's a middle path we can take. And again, even though this is the middle path, this middle path has been very less explored.
Are there any models based on rational adversary?
No, no. So at least in my work, at least in secure multi-party computation, except for a couple of references, there is hardly any work done in the rational multi-party computation. That's like a gold mine to explore. Right. So now you can see that there are three dimensions, right? Models of computation, where whether your circuit is Boolean or arithmetic. Dimension number 2, what type of network you have, whether it is complete network or incomplete network, whether it is synchronous or completely asynchronous or hybrid, and what type of adversary it is, whether it's a threshold adversary or non-threshold adversary, whether it's a polytime adversary or unbounded powerful adversary, whether it's a semi-honest adversary, whether it's a malicious adversary, and whether it's a static adversary and adaptive adversary, right? So you can see in each dimension I have 2, 5, 9, these many sub-dimensions. So how many dimensions I can study this problem? I have at least 90 different settings in which I can formulate this MPC problem, and I can study this MPC problem. And it turns out that it's not the case that if you design protocol for one domain, it simply carries over to another dimension. Each and every dimension brings its own challenges, and for that you have to come up with new primitives, new tools. And that's not the only way I can specify the different dimensions in which we can study the MPC problem. There are several other dimensions which I have simply skipped because of lack of time, right? So now what are the various attributes of any MPC protocol? How do we judge whether MPC protocol 1 is better or whether MPC 2 protocol is better? So there are 3 parameters. It's something similar to how do we measure the running time of 2 sorting algorithms. And we have this notion of space complexity and time complexity, right? We judge the merit of 2 algorithms by their running time and space complexity. In the same way, we judge 2 MPC protocol based on the parameters. So the first parameter is how much resilience my protocol is, how much resilient it is, how many bad parties it can tolerate, right? If I am in the threshold model, what can be the value of T? What's the relationship between T and N? If I am in the non-threshold model, what's the relationship between N and the adversary structure, and so on? Then what kind of security protocol you are aiming to achieve, whether you are interested in achieving a computational security, whether you are interested in achieving robustness, non-robustness, fairness, unfairness, so on. That means what kind of adversary you have, how much corruption it can have. Depending upon that, the level of security that is achieved by your protocol also varies. That means if you are assuming a polytime adversary, then the notion of security will be different compared to the notion of security that you achieve when your adversary is computationally unbounded. And of course, the third parameter is how much communication is required from the honest participants as part of your protocol. That's the communication complexity. How many rounds of interaction is required by the honest participants in your protocol, how much computation is required by the participants in your protocol, and so on. So these are the set of third parameters. So now what are the fundamental questions associated with MPC, right? So first fundamental question number 1 is the issue of possibility and impossibility, namely what's the necessary and sufficient condition. That means you fix your model first, say asynchronous model, computationally unbounded adversary, threshold setting, full stop. This is the adversary I am considering. Then for what values of n and what values of t you can design a protocol. It's not the case that for every value of n and for every value of t you can design a protocol. It's something similar to that we have this so-called nice bounds encoding theory, where we have dependencies between the size of the message, the length of the code word, and how much error adversary can introduce. Depending upon the relationship between these 3 parameters, you can define whether the message is recoverable or not. The same, we have the issue of possibility here. So for instance, in the synchronous network, if I am assuming adversary to be computationally unbounded, I require n to be greater than 2t. Whereas if I go to the, say, asynchronous model, I require n greater than 4t. So you see that the relationship between n and t completely changes if I just go from one model to another model. So you cannot say if I solve a protocol or design a protocol in the asynchronous model that can be simply adopted in the other model. It may the translation will hold in the one direction but not in the other way around, right? The second question is the question of efficiency. That suppose you have answered the issue of necessity and sufficiency. That means you now know that in your network you have the desired relationship between N and T, that you can design a protocol. But can you design an efficient protocol? Where by efficient I mean whether can you design a polytime protocol or not. That's the question of efficiency. And the most important question is the question of optimality, where we ask, is my protocol the best possible protocol in terms of all the parameters? Does it require the minimum number of rounds? Does it require the minimum amount of communication? And does it require the minimum amount of computation? Again, you can imagine, you can compare this something similar to the sorting algorithms, right? Before merge sort or quick sort came, people had n square algorithm. Then someone improved it to n log n. But after n log n, there is no scope of improvement because we have this lower bounds which says that any comparison based sorting algorithm need to do n log n operations. That's why we say that asymptotically merge sort and quick sort are asymptotically optimal. We cannot do better than that. In the same way, when I say the question of optimality, we would like to prove lower bounds on the minimum number of rounds required for any MPC protocol, minimum communication required in any MPC protocol. And once we have those lower bounds established, we would like to design a protocol whose actual communication, actual round matches those lower bounds. So that's the question of optimality, right? So what's my research interest? So I am a theoretician by training and only fundamental and abstract questions interest me. So Shesha is very smiling, right? So he knows this very well. And my main focus is to answer some of the questions of possibility, feasibility and optimality of MPC in various settings. My recent focus is on efficient MPC in the asynchronous network and in the partially synchronous setting. Sorry?
The earlier statements you made to your slide, does the if and only if mean optimal?
Yes. So that's a yes, optimal between in terms of resilience. We have lower bounds for communication. For that N and T, yes. Yes, 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 yes. Right. So some of my recent works are on efficient MPC in the asynchronous setting and in the partially synchronous setting. So what I will discuss now is just a very high level overview of just my results, my statements, result statements. So I have several results, but what I will do is I will just highlight the results which I have published in A-star avenues. So this is one of the results got published in PODC 2014, where we investigated the resilience for asynchronous MPC protocols. So there is a well-known lower bound which says, or necessary and sufficiency condition, which says that in the synchronous domain you require minimum T to be less than n by 2, whereas in the asynchronous domain you require T to be less than n by 3. So you can see that there is a clear discrimination in these two worlds. So our result in the PODC paper was that we showed that if you somehow enforce non-equivocation, so non-equivocation means preventing a bad parties from sending conflicting information. So remember, if my adversary is a malicious adversary and if he is supposed to send a value X, he may send one version of X to one honest guy and another version of X to another honest guy. And that's called equivocation. In the PODC paper, we showed that if there is a mechanism to enforce non-equivocation, right, then you can even design MPC protocol in the asynchronous world with T less than n by 2 without adding too much overhead. That means now you have the equality between the two worlds. In another work which got published in IEEE Transactions on Information Theory in 2016, we explored asynchronous MPC protocols, where our goal was to design better MPC protocol which has better communication complexity. So the previous communication complexity was n squared times the circuit size, and we reduced it to n times the circuit size. And the importance of our result is that our protocol is scalable in the sense, if you look, the total communication across all the n parties is n times the circuit size. That means per party is almost constant if you keep on increasing the value of n. In that way, our protocol is scalable. That means if you keep on increasing the value n, if you keep on increasing the value of n, that's not going to affect the communication complexity. Whereas if you have a quadratic communication, it has a quadratic dependence on the number of parties. That means if your number of parties increases, the communication also increases. But if my total communication is n times c, per party communication is almost asymptotically constant.
Here would the message size not increase?
No. So that means you are interested in the poly fact?
No. Message size, each individual message.
No, it won't. Interestingly, no.
My intuition would say
No, no, no. So that's what. So that's the novelty of our work. We showed that we actually gave a very nice framework for designing information theoretically secure MPC, which is far better than the previous protocol, and that's why we end up having overall communication complexity less, as well as the message complexity also being less. Right? And this is a very recent work where we studied the problem of crash-tolerant distributed agreement or distributed consensus in directed graphs. So let me define the problem. So we have a set of n mutually distrusting parties, and t of them are bad here, and they are bad or they are corrupt in a fail-stop fashion, or they may simply crash. That's a weaker form of adversary, but they can simply crash here. And each party has a private bit as its input, and the goal is to design a protocol such that at the end of the protocol, all the parties output a common bit. That means we want that even if there are t bad parties in the system, finally all the good parties should agree on a common bit, call it B, and that B should be the input of at least one honest participant. That makes the problem very interesting, right? So most of the work in the Byzantine agreement, in the crash-tolerant setting, crash-tolerant domain has been done, assuming that a network is a completely it's a complete network. That means every participant is directly connected to every other participant. What we have done in this paper is we have studied this problem in a very general setting where we assume that a graph is an arbitrary directed graph. That means you do not have pair-wise channel or pair-wise link between every pair of participant in the system. So we gave round optimal protocols, and the optimal protocols which requires the minimum number of rounds, we also put the lower bound, and that's the work which got published in DISC 2017. No, it's a strongly connected graph, that's all. That means you can reach to every other guy, but you do not have a direct channel between every pair of entities. You do not have a direct link between every other. So you cannot directly send to everyone. Yes. 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 Right. Huh? So that's determined. So you need to have a minimum structure in your graph. So the necessity condition is that even if the set of t bad nodes crashes in your graph, the remaining graph should be connected with a source. That means it should have a spanning tree. Right. So that completes part 1 of my talk. Right. Now part 2 is conditional. So I have plenty of time okay. And I don't know whether you are feeling bored or not.
So you can live up to your promise.
Right?
You can live up to your promise.
But vacuously this statement is true. Right? So what I will do is I will discuss one of my very recent results, and it's not related to crypto, it's related to distributed computing. So this is on multi-valued asynchronous reliable broadcast in the asynchronous setting, which got published in ICD-CN. So here is a brief summary of the paper. In this paper, we consider an asynchronous setting with t less than n by 2, and our goal is to design a broadcast protocol. I will formally define what do we mean by broadcast protocol. So our goal is to broadcast an L-bit message with a communication complexity of n times L, and if we can achieve a communication complexity of n times L, that will be optimal in L, the message size. Previously, such protocols were there. Such protocols means protocols with O of n times L communication, but they were designed with t less than n over 3. So our main aim was to improve the resilience. That means we wanted to improve the resilience from t less than n over 3 to t less than n over 2. And that's what we did in this work. And the tools that we have used in this paper is a non-equivocation mechanism. Namely, we assume that there is a method by which I can restrict the bad parties from sending conflicting messages to different honest guys, right? So now let me formally define what is the broadcast problem. So you assume you have a complete network of n parties here, and they are connected by pairwise private channels. T of them can be under the control of Byzantine adversary. Namely, the T bad guys can behave in any arbitrary fashion during the protocol, and there is a dedicated sender, okay? And sender could be one of these n entities. The identity of the sender also will be known as part of the problem description. And his goal is basically to broadcast a message M. He has some message M of size L bits, and he would like to send that L bits identically to all the n parties. And this we would like to achieve even if the sender is potentially corrupted. Because if the sender is honest, then there is nothing challenging in the problem. He can simply send his version of the message to everyone else, that's all. But the problem here is that your sender itself could be potentially corrupted, and he may send different versions of M to different guys, right? So formally we would require the agreement property, namely at the end of the protocol, all the honest participants should output the same message M star, and that M star should be the same M if sender is honest. That means whatever message M the sender started the protocol, we require that at the end of the protocol, everyone outputs M star equal to that message. Whereas if the sender is bad, I don't know what is M star, the requirement is all the honest parties should output a common M star. That's the requirement from any synchronous broadcast protocol. And this is about the synchronous and asynchronous setting, so I believe I can skip that because all of you now know what's the difference between synchronous network and asynchronous network, right? So the only thing that you should remember is that if you are in the asynchronous model and if you are a party, you cannot afford to receive communication from all the N parties because messages from T parties may not come to you. So as soon as you receive communication from N minus T parties, you should jump to the next step of the protocol. You forget about what the T messages are. Let them come whenever they come. You simply don't consider them, right? So that's the property of asynchronous protocol. So now if I redefine the broadcast problem in the asynchronous protocol, I have a new property, namely the termination. So the termination guarantee is that, so remember if I am in the asynchronous model and if the sender is corrupt, he may not initiate the protocol itself. He may not send a message to any entity. Then in that case, you cannot say that the protocol should always terminate, right? So when I am defining the asynchronous reliable broadcast, there is a new property, namely termination, which has two sub-properties. Sub-property one is, if the sender is honest, I require that all honest parties should eventually terminate. Because if the sender is honest, he will initiate the protocol by sending his message to everyone, and as a result it's natural to demand that all honest parties should eventually terminate. The second requirement here is, if some honest party has terminated the protocol, it should be the case that every other honest party should also eventually terminate the protocol. So that's an additional property that we require from the broadcast problem in the asynchronous setting. Of course, the agreement and the validity properties remain as they were in the synchronous setting. That means we require that if at all honest parties terminate, all of them should terminate with the same M star, and that M star should be equal to M if the sender is honest, right? So this is a very fundamental problem in distributed computing, and there's a well-known lower bound result which says that you cannot solve the asynchronous broadcast problem if T is greater than equal to N by 3. In fact, our Srikanth has done a lot of interesting work in this domain. Many of you may not know this. Okay. So this was a lower bound which was proved way back in 1984, and there is a very elegant protocol attributed to Braca published way back in 84 where they showed how to design an asynchronous reliable broadcast protocol with T less than N over 3, and the communication complexity of the protocol is N square for one message. It means if the sender's goal is to broadcast one bit, it requires N square amount of communication. And interestingly, Dole et al. Proved that's the best you can think of. They proved the lower bound that any one bit agreement protocol, whether it be in the synchronous model or asynchronous model, requires omega N square amount of communication. In that sense, this is the best you can think of. Now, what is multi-valued broadcast, right? So imagine a scenario where sender has a huge message to broadcast. He no longer has a single bit to broadcast, he has an L bit message to broadcast. And in our MPC protocols, we typically come across such a scenario where a party needs to broadcast a huge message. It's no longer a single bit. So if the sender's goal is to broadcast an L bit message, one nice solution will be that you invoke L instances of single bit broadcast. You divide your message into bit by bit by bit and invoke L parallel instances of single bit broadcast. So this notation BC1 denotes that this instantiation of this broadcast is for one bit. So you instantiate L instances of broadcast, and if one instance of broadcast require N square amount of communication, L instances of broadcast will require N square times L amount of communication. Now what multi-valued broadcast aims to achieve is the following. Instead of broadcasting the bit by bit, the entire L bits, instead try to do the following. Most of the communication should be done over the point-to-point channel, and the instances of 1-bit broadcast should be done for something whose size is independent of L. That means you imagine that we design a protocol in a completely different way, where most of the communication is still over the point-to-point channel, and the instances of 1-bit broadcast are done for broadcasting something which is a polynomial in N. In that way, what we do is we achieve a communication complexity of this much, N times L, plus poly number of instances of single bit broadcast. And now if you instantiate these instances of broadcast by running the actual broadcast protocol for broadcasting these many bits, your overall complexity becomes N times L plus something polynomial. Now if you assume that your L is so large that it subsumes this poly thing, asymptotically the overall communication complexity becomes order O of NL. And that's what is the goal of any multi-valued broadcast protocol. You don't do it bit by bit and invoke L instances of broadcast. Instead, you instantiate instances of broadcast to do something whose size is independent of L. Right? So that's what is the rough idea of doing multi-valued broadcast. Yes.
Now, why is this useful? Because I would assume that the amount of the size of the message that I'm trying to communicate will typically be limited, whereas N is the
no. So that's what I'm saying. If my goal is to design an MPC protocol, say we come across scenarios where L is very large. It's of order N cube, N4, N5. So there, if I just do it bit by bit, I do it N power 5 times N square.
But in an internet kind of scenario, this won't work, right? Because then
depends upon.
My L is limited. N is what is.
No, it depends upon what is your L. You cannot always say your L is dependent.
N could also be smaller.
Your N could be small, your L could be large. So you have the trade-off. And you cannot say your L is always small in the internet. If you consider state machine replication kind of scenario, my L could be the entire database. Right? So there are prior work which does multi-valued broadcast. That means it achieves O of NL communication complexity, but most of them are in the synchronous setting, and the only work in the asynchronous model is with t less than n over 3. And our goal is to actually achieve the same with t greater than equal to n by 3. That means something which is more resilient.
Are there algorithms which try to achieve the other kind of trade-off?
Yes, these are the results. Yes, all these achieve communication of O of NL plus poly n.
No. So are there other ways you keep the N
Fix it.
linear and L you let it go?
So n linear in what? So n is my number of participants. So
I don't want it to be a high degree in the number of participants because I expect the number of participants to be large.
So there is no work like that here. No, yeah. Right. So our goal is to design an asynchronous.
Replicating it L times to do that, right? Where if L is small, then you replicate L times. So he's trying to indicate that L is small and L is large.
Yeah, L is small and N is large.
L is small, n is small. N, the number of participants. The size of the message. A number of participants is large.
Size of the message is small.
Then you can do the typical bit broadcast protocol. Yes. Yes.
Yes. It will be N squared again, right? So it will be N squared. I can't afford N squared because N is huge.
Yes, asymptotically n square n times L is always better than n times L if I'm measuring in terms if I'm fixing n as the parameter. So L part is fixed. If one protocol is n times L and another protocol which is n square times L, of course the n times L is better than n square L.
But it is NL plus a poly N.
So what is that poly? That poly determines, yes, agree. So it determines, okay, so let me directly jump into my result. Okay, so wait. Yeah. So finally our protocol has communication of NL plus n cube k. Okay, so that means if I assume that my message size is at least n square k, right? If I assume that my message size is at least n square k, then this n times L subsumes the poly thing as you are saying. And then I can say that my overall communication complexity is O times NL. That means if you ensure that your minimum message is at least n square times kappa, then my protocol is better instead of doing it bit by bit by bit.
Overbound is n squared, right?
That is for one bit. So I am not beating the lower bound. N square is always there. I am not beating the lower bound. What I am doing is, if you do it in a different way, where you don't do it bit by bit by bit, most of the things still happens over the point-to-point channels. It's only for doing stuff once in a while that you invoke the broadcast protocol, which is having complexity n square. But the number of such things which you do occasionally, which you do once in a while, is too less actually. It's only poly number of times. Right. So there are asynchronous broadcast protocols designed beating the t less than n by 3 bound, and this was the work published in Pod C12 by Clement et al., where they show that if you assume that bad parties cannot equivocate, that means they cannot send conflicting versions of the messages to different honest parties, then you can beat the t less than n by 3 bound. So what is the equivocation? Equivocation means if the sender is corrupt, it can send 1 to one honest guy and the bit 0 to another honest guy, whereas non-equivocation means he cannot do that. Now notice that non-equivocation does not mean that he sends the message to both of them. Non-equivocation means to whoever it sends, he is sending the right version. He might end up sending to a subset of the honest guys, right? So, and there are varieties of proposals to implement this non-equivocation mechanism. Namely, you assume you have some kind of trusted hardware, or you have some kind of attested append-only memory. So there are ways to implement this non-equivocation mechanism. So on a very high level, the idea behind a non-equivocation mechanism is the following. Every message M which a party is supposed to communicate to the other party will be authenticated by a counter. You can imagine K to be a counter. And this values of counter will keep on increasing after each protocol step. That means if I am in the ith step of the protocol and if I am supposed to send a value, some message M, that message M will be associated with a counter K. And everyone will know the value of this counter K. So every message which this party is supposed to send in this protocol step K will need to be attested by a trusted hardware with which this adversary cannot mess up with. And as a result, what is going to happen is any message which is received by any participant in the kth step will be validated with respect to this counter K. So what it ensures is, if for the same value of counter K, it tries to send M and M dash, that's not going to be possible for the bad guy because its hardware won't support that. Because once it attached a message with the counter K, it's automatically going to increase the counter to K plus 1. That means it's expecting that his hardware will be now attesting a message with K plus 1. That means with the counter K or with the key K, it's only one version of the message which can get attested. But as I said, even if he attests a message with the counter K, it does not guarantee that he is sending the message to everyone. He may end up sending only to a subset of participants. So it was argued in this paper in Pod C12 that to ensure that if one guy receives the message and he can transfer it to everyone else, this authentication mechanism should support transferability. That means it should have the same structure as signatures. That means if the hardware of the sender attests a message with the counter K and it gets verified by PI, it should be possible for PI to further transfer it to someone else on behalf of the sender. So that's a transferable non-equivocation mechanism. Right? So if we have a transferable non-equivocation mechanism, then you can think very quickly that there is a very simple asynchronous protocol, even with t less than n. That means even if all the 99 guys are bad and there is only one good guy in the system, still you can design an asynchronous broadcast protocol. And the protocol is simple. Imagine sender has a message of size L bit. What it can do is it can send the message non-equivocably to every guy. That means it can attest its message M by its hardware and send it to everyone else. Now due to the asynchrony, it may happen that some parties receive the message, some parties do not receive the message, or if the sender is bad, he may not send the message at all to anyone. So we add one additional round of communication where we say that whoever receives the message, just forward it to everyone else on behalf of the sender with the same non-equivocation tag. And that's possible because of the transferability property of the non-equivocation mechanism. So if I am P1 and if I receive some message from sender which I validated, I simply relate to everyone else, which ensures that it's not only me who has received the message, it's every other honest party in the system who will end up receiving the message. So that will be the second round of communication. So the overall communication of this protocol is n squared times the message size, because in the first round, sender sends it to everyone, so it's linear in the number of participants, and then every party, whoever receives it, relate to everyone else. So I have to relate to all the n guys, P2 has to relate to everyone else, that's why it's n squared times L, right? So the main question that we address in this question is, can we design a multi-valued asynchronous broadcast protocol with O of NL communication with t greater than equal to n by 3. So these are the results which are there in the paper. So we indeed show that if you assume t less than n by 2, and if you are in the non-equivocation if you are given some kind of non-equivocation mechanism, we can design a protocol with communication n times L plus n cube k. That means if you assume your message is minimum n square k, asymptotically the communication complexity becomes n times L, and that's how we achieve the O of NL communication. So I think I should skip the technical details because they are too technical, right? So if you are interested, you can go through the paper. Let me so these are the future plans. So as I said, I would like continuing answering the question of possibility, feasibility and optimality of MPC in several other dimensions which are not yet explored. And recently I started working and exploring blockchain as a platform to see what kind of distributed computing tasks we can efficiently do using blockchain as a platform. So I am not interested in the crypto aspect of the cryptocurrency. I am just interested in the blockchain as a platform. And of course, as I said, the ML is necessary for survival. So I also started exploring the area of privacy preserving ML. Thank you.